Welcome to Week 8 of the course. We're going to talk about natural language processing, NLP, and robotics. So I think it's the Grace Hopper chapter in the AIQ book. I think From Alexa to Grace is one of the interesting chapters. So let me quickly talk about this. So one of the key algorithms or original algorithms was Google's word-to-vec algorithm. So the first thing to realize is you have to convert words to vectors so I can then pattern match and manipulate them as numbers. And again, as I said, deep learning is the process that people will use, and the BERT algorithm that gets used. I think it stands for bidirectional encoder representation transformers. So has a rather long acronym. And there's lots of business applications ranging from classification to language translation to text summarization and such problems. Again, a little bit of history. If you remember back to Jeopardy about 10 years ago, IBM's supercomputer Watson beat the then champion Ken Jennings, and there's a link to that. So it's very interesting to see how quickly IBM's Watson could understand the question and then actually come up with the answer to the question. So that's a great link. Another really cool link, if you've never seen it before, is the Google Assistant link, where people are phoning up to make a restaurant reservation, and it's a computer phoning up, and it's quite interesting how the computer responds to the person making the reservation. So again, the idea is an input, but now input is speech, and again the output is the computer just really trying to describe what's being said. Here's a funny text analytics application. If you go to this website down here, it's from ratemyprofessor.com, and believe it or not, when people are rating their professors, the term good teacher is used the most for mathematics and engineering professors, and the least for philosophy and anthropology. So you can go to that website and play with different texts, and it's basically a text mining tool to just to see what words come up most frequently. Okay, so natural language processing has grown. Linguistics has grown over the last 30 years tremendously. Nowadays, it's conversational AI. Again, NVIDIA is and Google are the two main companies. And again, as an example, can a machine really write an article for the New Yorker? You might want to take a look at that link, and it's already computers are generating sports scores, sports summaries, and can it actually write articles for magazines? Can it write books, for example? Quite powerful how it's done. Now, in the last 10 years, there's been a whole sequence of ways of doing these language processing problems, and really the most current one is more like a brute force type approach. So, and it's known as a semi-supervised learning approach, where the idea is to take a massive big data set. So remember, companies like Google have huge data sets. So take a big corpus of documents, knock out about 15% of the words, and then just to fit what's known as a forward feedward neural network, an architecture with nothing too fancy, and try and fill in the missing blanks. Can I fill in the missing words? And rather surprisingly, these types of algorithms have become the winning algorithms. And by winning, it's just looking at that out of sample prediction error for doing these pattern matching problems. So this filling in the missing data, it doesn't need labeled data. Really, is the big insight. You don't need to know what the labels are. So that's a big help. And really, it's more a brute force approach. And this BERT model that's become popular that Google uses has about 350 million parameters, maybe a few more. So again, brute force. And why does it work? Well, there's not that many words in the English language, for example. I think someone like Shakespeare knew 250,000 words, but we're not all Shakespeare. I don't know what the typical person knows, but maybe say 20,000 words. And of course, maybe 5 to 7,000 of those turn up 90% of the time. So the prediction problem is really just predicting 7,000 or so words with very high probability. And these brute force algorithms seem to now be doing the best rather than more tailored algorithms. So I thought that was interesting. So essentially, that the trick is you train your model by filling in the missing blanks. Now, of course, the downside is that you need big data sets, so large empirical data sets plus good empirical pattern matching scores. The architecture for the deep learning model doesn't have to be too complicated. Gives good outcomes. And again, I think now there's GPT-3. The type of algorithms you'll see people talk about are GPT-3, BERT, word2vec, those types of things. And again, the whole goal. Remember the Bayesian personalization part of the course. That language models will become more personalized. I think Google has a website where it'll translate you speaking into a different language, but will also have you talking with your type of accent in that language. So it's quite remarkable what can be done. Also on the with every positive, there's generally a negative. So chatbots and deepfakes have become a big deal. A couple of my favorites. So there's a Chinese AI news anchor, which is quite interesting. On the other side of the coin, there's a deep fake for people getting Barack Obama to say what people wanted to talk about. And maybe the Silicon Valley episode, season 6, episode 1 is the one to look at, where Guilford basically builds himself a bot to reply to all emails and questions that people have for him, so he doesn't have to do any work there. So chatbots and deepfakes is a big area. Now, one thing that interested me was what was one of the original applications of natural language processing, and it was actually David Bowie. So again, if you click on this link here, David Bowie built a machine learning algorithm called Verbicizer to try and help him write his songs. So lots of the wording in his songs was created by an algorithm, and he would just have the algorithm randomly throwing out different combinations of words from different articles from newspapers, and he would then see if he could put emotion and whether that sequence of words would mean anything to him. And so a large portion of his songs are written with this idea of natural language processing and machine learning. So I thought you'd find that interesting. And as I said, the latest algorithm, so 2021, is something called the BERT algorithm. There's the full definition of it. And again, the idea is just to get better searches for people. So can you get medicine for someone at a pharmacy? Nowadays, Google will come up with a better answer rather than just talking about whether a prescription can be filled or not. So again, there's always this idea of improving algorithms. A 1 or 2% improvement can mean billions of dollars for companies as big as Google. And so that's sort of interesting. Now a sort of competing set of algorithms, something called GPT. There was GPT-2, now there's GPT-3. There's a company called OpenAI, which to look at. Elon Musk invested in it at its infancy, and more recently he's had some more critical things to say about it. So take a look at OpenAI and GPT-3. If you want to go into the AIQ book, I think it's James did a fabulous job of explaining natural language processing. It's one of his fields of research, so he's one of the world's experts at it. So I sort of defer you to the book. So one of the interesting things of these big empirical data sets, a little bit like the chess problem, is in the old ways of doing linguistics, it was having to write down lots of rules. And the trouble is that the rules just get bigger and bigger and bigger, special cases, and it's tough. And so this empirical pattern matching tended to work well. So the chapter to read is From Grace to Alexa. Just to give a little bit of an idea, These machine learning models are much more flexible than these rigid hand-coded rules. They're probabilistic rather than deterministic, and they're more bottoms up. They're based just on empirical data set rather than a profusion of rules. So speech recognition, speech translation are the big problems. If you want to get sort of an idea of how natural language processing works, you have to first of all convert words to vectors. And again, this is, James explains it via the maths of 20 questions. So you have a word here that you want to represent as a vector. So these would be features. So these would be like your known features in the algorithm. And essentially you're scoring a word relative to its sort of features. So these are really just the weights. And here I've just done a simple case where it's pretty clear the weights are 0 or 1. And these weights will uniquely determine what the word is. So the representation of Rafael Nadal, for example, would be the vector 111100, given that feature basis. And remember, one of the tricks of deep learning is how do I find the feature basis? So one of the great things with them, you find this empirically. You don't have to give it the rules to begin with. Now, of course, in general, things are more complicated. You play this AI for 20 questions, but it's not a 0-1. It becomes probabilistic. So those weights become a bit more blurry. So if you look at the example out of AIQ, you'll see a slightly more blurry set of weights. And again, one of the interesting things is that once you've converted words to vectors, so Google Word to Vec, you can then sort of do equations in words. So you can then ask the computer, London minus England plus Italy equals what? And of course, it would be the capital of Italy, would be Rome, right? So in some sense, once you've converted words to vectors, then once you've done pattern matching and found what the features are, you fit your deep learning model, you can then essentially, it seems as if the machine has intelligence. In a sense, it's really just a massive big lookup table where you've basically pattern matched and it's filling in the differences. So, Canadiens minus Montreal plus Toronto will identify the Toronto Maple Leafs. And again, remember, everything is sort of probabilistic in these frameworks. Nothing is that clear-cut 0-1. So when it's got a sentence and it wants to fill in how lovely it smells like a rose, it's a probabilistic assessment. And, other words have much lower probabilities. And then, some of them are subtle, right? Is it rose or is it rose? So again, the algorithm should be smart enough to be able to figure that out as well. So, really the natural language processing revolution really started with this Google Word to Vec, and then has sort of ended with these BERT type models for doing, very high scale data sets and very sort of clever high scale pattern matching. So that's really sort of what's been going on. And again, how does it train? How does it get context? Again, if you go to Google and search BERT, you'll see people talk more about how you train a Word to Vec model, how you sort of fill in the missing blanks in a BERT model. Okay, so that was a very quick, brief overview of natural language processing. Clearly, speech recognition, just like image processing, is one of the holy grails, and it's been a research area for many, many years. And the company that has the best speech recognition, Alexa or OK Google, for example, you can see there's a lot of competition for getting better and better algorithms for doing speech recognition. Okay, now let me do a second area of applications, which is sort of an interest of mine. So robotics, what goes on in these automation robotics type problems. And I got interested in this by looking at some of the original work on it. So remember Claude Shannon. There's a beautiful video on Google where he builds a little automatic mouse that he calls Theseus that's trying to get out of a maze. And just by trial and error, remember the other nice thing of computers is it can try and fail 1 billion times, and as long as it gets a solution 1 billion times and 1, then it's found the optimum solution. So if you Google Claude Shannon Theseus, you'll see his original how does a mouse solve getting out of a maze purely by trial and error? And then the original driverless car was something called the Stanford Cart. I think the New York Times has a very nice article about that. And somebody called Hans Moravich. Again, there's a chapter in the AIQ book on robotics and driverless cars, talking about simultaneous location models. So again, that's sort of interesting. And really, self-driving cars are just the beginning. So if you can do the image processing or video processing problem, you can then solve what's known as the optimum control problem of how you should drive your vehicle and such things. What's the angle of the steering wheel and how quickly you should drive the car. Other sort of fun examples are sort of sports ones. Toyota built a robot that could instantaneously throw 3-pointers, so that was sort of interesting. I'm a big golfer, so there's an interesting video where Rory McIlroy plays a robot at golf and tries to hit a golf ball into a washing machine, which Rory was famous for doing when he was a kid. There's the robot backflip video. Again, if you start to watch these robotics ones, you get a little bit scared. There's also lots of ones where the robots fail to do things like open doors and they fall over because they're not balanced correctly. But essentially, you can solve quite complicated problems. There's the link to the Stanford Cart, and there's one of the original founders, Hans Moravich. And I think what's interesting is it took 15 minutes of calculation per image. So I think it took like 6 hours for this car to go across the room at Stanford. So just to imagine from the 1970s, just to imagine in 40 years what the increase is from Hans Moravich's vision of the Stanford Cart to say a Tesla autopilot driving car is really quite remarkable. So if AI and image processing has the same increase in the next 40 years, then it'll be quite remarkable what people can do. Now, another interesting area, so Google DeepMind is really one of the forefront companies in this, is something called Q-learning, or essentially implementing the math that somebody called Richard Bellman started in the 1950s. So how do you optimally solve decision problems? And again, OpenAI works in these things, and people have implemented them on video games. If you click on the link up here on the slides, you'll see one of the first applications to Atari Breakout. So here's these simultaneous location and mapping problems called SLAM problems. There's also Bayesian learning involved, as in all of these problems. So what's the optimum update rule from one image to another image? So first of all, you have to identify things and you have to map to the decision problem. So there's an interplay between these things. Copenhagen's an interesting city that has lots of bicycles. And again, smart cities is maybe another area of application. I know NVIDIA and Google have teams of people work on these things. Whether and how it'll come to fruition is an interesting problem. I think Google tried to build a smart city in Toronto. I think Bill Gates is building a smart city in the desert somewhere in Utah. And so there are these sort of futuristic cities that people are trying to build based on these types of things. So that's sort of interesting. If you want to see what Tesla does, there's somebody called Andrej Karpathy. And so if you want to try and understand how the Google autopilot, I think it's good for, when you're sitting in a driverless car, it's good to understand, what does it know and how does it work. So there's a nice link to the Tesla presentation. And again, the basic idea is sort of quite simple. Sometimes it's called learn from the best. There's something called a policy function. We'll talk a little bit more when we do chess. Essentially, what's the output? The output in a driverless car is just what's the angle of the steering wheel and how fast you go. And what's the input? A whole bunch of cameras or a whole bunch of sensors. And people argue over whether you need LiDAR or not LiDAR to help you with depth and color. And so there's an output, there's the input. You've got some form of video or sensor input. and it's going to go through one of these deep neural networks to decide what your optimum policy is. So given what state of the system you think you're in, and again, that can be a very high dimensional space, what's your optimum action? So if you think someone's running in front of your car, you clearly want to stop the car quickly. So identify what's in image and identify your outcome. And of course, if you read the AIQ book, there's a couple of examples where for example, if everything's snowing and all signs and all road marks are not available, snow makes things a bit harder. Things like kangaroos, believe it or not, make things harder because they jump up and down in front of you and they go from large to small objects and hard to see what's going on. But that's the basic idea. And of course, you want to avoid crashes. You want to avoid things on the right, and you just want people to be driving safely on the left. Okay, so another area which is interesting is sort of energy efficiency, energy markets. One of the first applications that Google DeepMind came to was how to cool all their Google servers. And I think there was something like 14 different variables that you could control, and it wasn't obvious given the aerodynamics of the data center how to do that. And so they just collected a big data set and they run one of these deep reinforcement learning models on it. Hey presto, they found a bunch of settings that didn't make too much sense to them. But of course, you just empirically try it. And so when they tried it, there was a huge big drop. And so a big gain in efficiency. And when they went back to the old settings, back up it went again. So it wasn't purely by random chance. So just by collecting a big empirical data set, doing some pattern matching and finding the optimum policy of how to set the settings for these 14 variables, there was a dramatic savings in cost. One of my co-authors, Vadim, and my son, Michael, I persuaded my son to get into deep learning. So if you go to the web, you'll see Michael and Vadim working on deep learning for energy markets. So I'm doing my bit to persuade people to apply deep learning to as many markets as possible, and I hope you guys do as well. Another quick one slider. If you're used to these old applied math problems, they can be very complicated to solve. Formula One driving problems, or one of the famous old what's known as the three-body problem. And again, if you just mathematically try to solve these things, it's a nightmare. Finite element analysis or solving very complicated math equations. But hey presto, if you simulate out a bunch of paths and just fit a deep learning model, the pattern matching works better than theory. So what's the motto there? That maybe it's not a good time to go in to do a math PhD in terms of equations. Maybe it's a better time to go do a math PhD or go do an AI PhD and do some deep learning. Okay, I haven't really talked too much about the math of it, so let me just give you a very quick overview, and then we'll talk a little bit about Google DeepMind and chess. So really, the equation that's being solved is something called Bellman's equation of optimality. And really what people are trying to find is something called a Q matrix. And it sort of makes a lot of sense that if you've got some problem, driverless car or playing chess, you have some state of the system. Remember, on the chessboard, there's 10 to the power 152 possible states, and you've got some possible action. What's my next move? And you just like to know a massive big matrix of all possible combinations. And then you could look into the matrix, and for example, you could find optimum policy. So for a given state S, you could find what's your best optimum action to do just by looking in that massive matrix and working out the maximum. And then if you plug that into the Q matrix, you could then find the value function. So remember, Bellman's principle of optimality is no matter how I got to that state S, I should act optimally going forward. So I should calculate A star, plug it in, and I should see what my value function is, V of S. So mathematically, in some sense, a simple problem. What's difficult is that it satisfies a rather complicated equation. So let me just super quickly explain that. So the Q matrix at current time t is instantaneous utility plus what's known as the continuation value. So if I'm at state S and I do action A, there's a certain probability of generating a new state S star. And then remember Bellman's principle of optimality, I'm going to act optimally going forward. So I would need to know this continuation value here, and then I would just add in expected value over all possible states. So it's what's known as like a nonlinear difference equation for, or nonlinear integral equation for the Q matrix, and so it's tough to solve that. And so there's iterative algorithms, so value function iteration or policy function iteration for trying to solve that. But so what's sort of interesting is all of these problems really come down to that one piece of math. It's just a question of implementing, and deep neural networks become valuable for doing that. In particular, this stage here will be solved. Both of those steps there will be solved by deep learning. There'll be a deep learner for the policy function, and there'll be a deep learner for the value function. Sometimes people call this reinforcement or Q learning. Amazon Web Services, Google. There's always this issue of what to show people on the web as they click through adverts. So there's a huge big field there. There's another big field of how do you actually calculate these things. So something called the policy gradient and something called stochastic gradient descent. I'll leave you to enjoy yourself and go to the web and search for these things if you want to learn more. Okay, so let me sort of finish the robotics with a little bit more of an in-depth look into deep learning and chess. So remember, we talked about this before, that the original approach was to take a whole bunch of human games. I think it was 23 million human games, run logistic regression, try to predict what probability a grandmaster move would be. 57%, I think, was our example, and then off you go. Well, instead, David Silver at Google DeepMind had a different idea. He was like, okay, why don't we try and solve Bellman's equation, but using deep learning? And instead of, we'll first of all start with an objective function of maximizing the probability of winning. And then we'll use what's known as rectified linear neural networks to find value functions and policy functions. I've got some graphs coming up. And then simply this idea of the computer will play itself a billion games. So it'll start off as a very bad chess player, and as it learns, essentially, a dot in very high dimensional space of whether it won or lost, it'll empirically know whether it won or lost, and then it'll be able to go back and figure out, okay, here's what optimum policy and value function I should have used. Okay, now, one of the, I think, Magnus Carlsen beat Bill Gates in, I think, 9 moves on Norwegian television in like 7 seconds. So if you want to see Bill Gates lose at chess to the world champion, it's a interesting video to look at. So I'll leave you to click on that link and enjoy. Okay, so let's talk a little bit about the AlphaZero algorithm. And it's a 2-minute trailer to a movie. But AlphaGo was an algorithm originally designed for Go. But of course, the same idea is just a deep neural network with radio activation functions can be used to do chess as well. And the rather interesting thing that Google found was it's amazing how quickly it was able to learn the game of chess, even though chess is a pretty complicated game for humans to play. And remember, the whole idea, it's all empirical. You just simulate billions and billions of games. You see who's winning, you see who's losing. You then use the deep neural network trick to essentially do interpolation, essentially to approximate the value function and policy function, and then you come up with an optimum rule. And as computers get faster, and as you add more parameters to your deep learning model, the ratings of these chess algorithms will slowly go up. Okay, so let me give you a couple of little pictures. So this is from a Go board. So Go is a game where you put white and black stones down on a board, and you try and encircle the other person's area. So can the whites encircle the black stones down here? And so this would be a position of the board. So this would be a little S. And at the end of the day, at the top, we want an evaluation of that position. Are we winning or losing? So do we have a 90% chance of winning from this position, or just a 10% chance? So theta of parameters of my neural network, essentially given a state S, I want to estimate a value function V of S. So I give it a billion states, 10 to the power 6. I fit a deep neural network, which means given any other state, I can also, even though I haven't seen that state, I can attach the value function to it. So in some sense, deep learning is what's known as an interpolator. I want to pattern match what I've seen. I know what's winning and losing for a billion states, and I'll just use my deep neural network to interpolate for the other states. Now, why is that such an important thing? Well, remember that, even if I've looked at 10 to the 6 possible states, there's 10 to the, in Go, there's 10 to the 900 possible states. So a lot of work is done by deep neural networks in these things. So if you're not using deep neural networks, you're having difficulty doing that extrapolation. And again, a lot of the deep neural network is understanding spatial structure on a chessboard. Remember, the old-fashioned way was to value pieces, 1, 3, 5, 9 for a queen. Well, that's marginal, not conditional. And so you want the value to be done conditional to where the current state is. So really, it was the deep neural network or the neural network piece that made these chess algorithms so much more powerful. A chess algorithm that can just look forward 3 or 4 moves and do what's known as calculation, given the value of the pieces, can beat a human, but has no chance against these deep neural network type algorithms. And so people have moved more towards those. So there's one neural network for estimating the value function, and then vice versa, there's one neural network for estimating the policy function. Well, what do I mean by that? I mean my current state S, and I want to know what's the, where should I move? And again, it's probabilistic. Remember that the output of these algorithms is probabilistic. So, but 93% probability, I should put my next stone there. And again, there's an interplay between the two, right? As I fold forward, as I look forward in time, and I put in my optimum actions. Remember the Bellman equation. I'm assuming I act optimally going forward in time. So as I go forward in time, I then can fold back and work out the value function. So there's an interplay between those two functions. If I have a bad policy function, I'll have a bad estimate of the value function, and sort of vice versa. So there's some iteration to convergence, and that's why you have to simulate a lot of games, and that's why you have to fit your deep neural network and find out what's going on. So again, just to give you an idea that, if I'm looking at the chessboard, there's an exponential growth of possible strategies. So no computer can enumerate all those things. So it's an NP hard problem. So I need to have some clever way of cutting down the possibilities. So one clever way is what's known as, so it's called Monte Carlo tree search. So sometimes you'll see people call it MCTS for Monte Carlo tree search. And so you just have a stochastic rule for going down different branches. And if you're clever, you'll weight branches that have higher values for you, so you get to learn the optimum rule more quickly. And you'll sort of ignore branches where things are suboptimal to begin with, right? So Monte Carlo tree search. How do you need to reduce the depth? I mean, a chess game can go on for 60, 70 moves. Some of these computer games go on for way more, like 160, 170 moves. They become, it's hard for one of these computers to beat itself. So it becomes a harder and harder problem. Well, how do I cut the depth? Well, essentially, after I've gone down a certain depth here, maybe 4 levels, I actually plug in my current estimate of the value function. So rather cleverly, I don't need to go forward anymore because I've plugged in at this given state what my current value of the value function is. So that does a great job for cutting the depth. I don't have an exponential explosion of states going forward. And then how do I cut the width? Essentially, I use the policy function. Remember, the policy function is telling me in that Monte Carlo tree search what's the optimum path to go down. So the breadth of the network is cut by the policy function. The depth is cut by the value function. And that's essentially how the AlphaGo algorithm works. And as I said, really, without the neural network pieces, it's going to be difficult. And again, there's a lot of interest in robotics in reinforcement learning. How do I get a machine to do something optimally? There's generally an input-output mapping, image processing, or state of a system, and there's generally some optimum decision rule that I want my machine to do something. And people are trying to categorize which problems are easy and which problems are harder. One of the gold standards of how good can you get your algorithms to work is can they play these high-level video games? So I have little interest in these video games except the beginning ones in time, like Space Invaders or Atari's breakout, but things like StarCraft people have tried to do. And again, another topic, if you went on and did more advanced things in deep learning, you'd learn about these things called multi-arm bandit problems and something called Thompson sampling. Again, the Google or Amazon Web Services is watching you click through its website, and it's trying to decide, well, what path should you go through. So it's bandit problems is a bit like picking which fruit machine you should pick. So you've got one of, say, 10 possibilities. Which arm should you go down? There's something called a Gittings index, or a value for each possible branch that you can calculate, and off you go. There's something called Thompson sampling. So, in the future, there's a lot of uncertainty in these problems. So it's, they're not known given problems, but you want computers to solve these things. I think there's a discussion of Taobao, Alibaba's website. Alibaba has a huge bunch of data scientists that are doing these sort of grunt problems of, okay, let me try and optimize the path of going through Taobao and figure out advertising budgets for people. We're sort of coming near the end of this week's lecture, so just very quickly, driverless car is big. Now, you see driverless cars on the road. I think Google Waymo has been driving around Phoenix, Arizona, but it can also do simulations. So NVIDIA has a big group of people that have a driverless car simulator. Google Waymo has done like 9 billion hours of simulation. And I don't know how much driving you do, but my guess is 9 billion hours of being on the road. A little bit like the chess algorithm. You can see that these driverless cars would no doubt be a lot better than humans driving. There's another group of problems called learning to learn. Maybe we'll talk a little bit about it in next week. The next thing up from AI is artificial general intelligence. So can you come up with very general algorithms that once it can solve one pattern matching problem, it can solve another one without the need of human input? So that's another interesting area. I once met somebody that worked on this AI Deutsche Bahn railway track problem. So scheduling, how to do maintenance problems. There are these massive, big, edgy systems, transportation systems that clearly can be improved using machine learning techniques. Believe it or not, companies like Uber, companies like Didi use a lot of AI. Companies like Grubhub, tracking exactly where your food is, exactly what the how long will it take, what's happening. There's a lot of modeling from your phone to the output, whether you're on bicycle, whether it's being delivered in cars, ... So everything can be sort of tracked in real time. So there's groups of people that do these types of things. So yeah, GPS data, motion sensor data. You only look once algorithms, they're called YOLO. You only look once. Can you get these deep learning algorithms to work on your phone? Something called edge computing. NVIDIA is one of the experts at these types of things. So there'll be just, I don't know how many NVIDIA chips will exist in the world in 20 years' time, but my guess is it's an exponential number more than we currently have, because you want computer processing at the endpoint. I think I've already talked a little bit about Uber Eats and their machine learning models, so that's something to look at. Okay, so let me finish there. So we've finished our AI, and we have 1 week left in class. We'll talk about a lot of business applications and sporting analytics. So again, I hope you enjoyed natural language processing and robotics.